Hi everyone. So today we're going to talk about systems of linear equations and two variables. So before we actually get into how we would solve systems of equations with two variables, we first want to define what they are, and then we'll talk about the various ways that we can solve them. Okay, so to start off, we're going to say, okay, well, a system of linear equations so the definition of this is literally a set of equations, and this could be two or more. So anytime we talk about a system of equations, we're talking about a set of any number of equations, but we know that we have at least two equations that are linear and involve the same variables. So what we're trying to do here is see, we're dealing with the linear case. Now, do a system of equations always have to be linear? Of course not. So, and we'll see that we will come across those types of problems later on. But for now, at least for this section, we're interested in solving the system of equations that are linear, which, what does that mean? If I were to graph them, their graphs will resemble lines, right? That's kind of where it gets the name from. So, an example of a system of linear equations will look something like this. So if you have, for instance, x plus 2y equals to 7, negative 3x minus y equals to 10. So this is what a system of linear equations is, and hopefully you understand why in this case we need two equations, right? If I were to get rid of this and I gave you just one equation and I said, hey, solve for that equation, you'd say, well, the problem I have right now is there isn't a single solution, right? We can solve it in terms of, let's say, y is in terms of x and so on. So if I say, no, I literally want you to tell me what x and y must be, in this case, there's infinitely many possibilities. So if I want a single solution and I have two variables, then there should be two equations. So if I have three variables, there should be three equations. If I have four variables, there should be four equations, right? And so I'm not saying that we need to have always the same number of equations as variables. That doesn't always have to be the case, but we know that if I want a single solution, then yes, in that case I would have to have, if there's two variables, there has to be two equations, and so on. So our focus, as far as this section is mainly concerned, will be just for the two variables, two equations case. So our focus in this section will be to solve two linear equations of two variables. So that's kind of where we're headed with this, right? We're going to see something like this example, and we're going to be solving this. Okay, so before we do that, what I want to do is talk about the possible solutions we'll get. So what we're going to say is that when solving a system of equations, we will discover there are three possible outcomes. Okay, so what I mean by that is, and it's not like, oh, before we solve it, we'll know exactly which one of the three outcomes it will be. As we're solving it, it'll become more apparent as to, hey, which one of the three possible outcomes it is. So it's going to take on one of the three cases, and we'll break down all the possible cases we'll have when we're solving. So these solutions that we're talking about describe how many times and when I say how many times, I mean if any, right? They may never even we may not even get any solutions. The lines intersect each other. Okay, so a visual description of what's going on is this. We're trying to find the solution of these lines, and the solution is literally the points in which these two lines intersect each other, if they ever do. Okay, so my solution is pretty much saying how many times they intersect one another. And then we'll see that we could actually break this down into three possibilities. So here are the three cases. So case one is if the system has one solution. So what does that mean? Well, if I were to visually graph it, if I have a system of two linear equations, it could be one line going this way, for instance, and then another line going that way. And what is it that we notice? Where do these two lines intersect? At exactly one point. So this has just one solution. So if you were to solve the system of equations, you would just get the coordinates of that point. Because remember, whenever you're solving these, you're just literally solving when they intersect one another, or what are the points that they share. Okay, so that's literally what's happening. So the second case, which we take case 2, is if they have no solution or they're inconsistent, right? So this is basically, if you say no solution or inconsistent, that just means the same. They both mean the same thing. So a case like this would be if I have two lines that are practically parallel. And so what is it that you notice here? Why do these guys have no solution? Is because they never intersect. So notice how they never intersect. And you'll notice that if they never intersect, then you have no points that they share or that they have in common. So in that case, there is no solution. And here's the thing, like I am breaking down the cases for you guys, but in a minute, you'll see when we do some examples, you won't know which case it is until you get started in the solving of this process, of this problem, okay? So, the third and final case is so case 3 is they have infinitely many solutions. Or another way of saying that is, or if they are dependent. So if you think about it, how could we have two lines intersecting each other infinitely many times? And I'm sure you've already guessed by now, that would be the case where the two lines practically are the same line, or they overlap in some sense. So if you look at it, if I were to, let's say, graph both lines, they pretty much are the same line. So kind of what's happening is they overlap. And if they overlap, what does that mean? They intersect each other at every single point, right? So that's where we get our infinitely many solutions, right? And so we'll talk about, you know, how do we treat or how do we describe these solutions that are infinitely many? And we'll get into that, and it's not that difficult to do, okay? So now let's talk about the different methods we're going to use to solve linear equations. So there's two algebraic methods, which we'll talk about. So the methods of solving a system of linear equations. So the first method is known as and I'm sure you've probably heard this before as well, This is the substitution method, which the name pretty much should give away what we're doing, right? We're literally substituting to obtain the solution. So here are the steps that we're going to follow. So to solve a system of equations through substitution, we will follow these steps. So the first thing we're going to do is we're going to say, well, select one equation and solve for one variable. In terms of the other. So the good news here is which equation do you choose? It doesn't matter, right? Because I'm saying select any one of the two equations. And then which variable do you solve for? That also doesn't matter. So generally speaking, I mean, we definitely want to pick the equation that's simpler and the variable that's easier to solve for. So, but in all reality, it doesn't matter. So depending on which equation you choose, one might be more complicated to solve than the other, but in all honesty, they shouldn't be incredibly difficult. But it really doesn't matter which equation you choose. So once you solve for one of the variables, then what you're going to do is the expression that you solved for here, you're going to plug it into the other equation. So that's where the substitution comes in. So you're going to then say substitute the expression from step 1 into the other equation. And then at that point, once you do that, you'll have an equation with one variable. And then so what you're going to do is, and you're going to solve for the variable. So once you solve for that variable, that means you already have one of the variables or the solution to one of the variables. Now, how do you solve for the second variable? Now you go back and substitute back into the original equation. So then once you do that, we're going to then say substitute the variable you solved for in step 2 into the equation, into the equation that you solved for in step 1, into equation from step 1, which will then complete the process, because then you solved for both variables, which will complete the solution for the system. Okay, now keep in mind that you don't have to write these 3 steps down when you're solving these types of problems. I just kind of numbered it for you just so you see the process we'd follow. So let's look at our first example, and we'll use the substitution method. So we would say find all solutions of the system (5x plus y equals to 2, 3x minus 2y equals to 22. So what we do is, just going through the steps, is we're going to take one of these equations and solve for a variable. So by looking at this, to me, grabbing the first equation and solving for y in terms of x, that's the easier way to go about it. So if I take 5x plus y equals to 2, and I solve for y. All I have to do is subtract 5x from both sides, and what do I get? Y is equal to 2 minus 5x. Now once I have that, then I go back to the equation that I didn't use, and in place of y, I'm going to replace it with 2 minus 5x. And by doing so, which this is where the substitution comes in, so then if I take 3x minus 2, except instead of the y, now what am I doing? I'm plugging in 2 minus 5x. I'm substituting 2 minus 5x. That equals to 22. Now if you notice what happened here, I have a single variable. So now I'm going to proceed to solve for x. And once I solve for x, I get, if I distribute, I get 3x minus 4 plus 10x equals to 22. Then we see that 3x plus 10x is 13x minus 4 equals to 22. Add 4 to both sides. Then we get 13x equals to 26. Divide both sides by 13, and we get x is equal to 2. And if x is 2, now how do I find y? I plug it in there. So I have y equals to 2 minus 5 times x, as we found earlier, except x is now 2, so if I plug in 2 there, I get 2 minus 10, which is negative 8. So notice how I got one solution in this case, right? Because my solution is what? 2 comma negative 8. So in other words, what are we saying? These two lines intersect at the point 2 comma negative 8. And so this was, from the three cases that we talked about, it was the first case where we had one solution. Okay? So let's move on to the next method of solving, which would be through the elimination method. So this also is pretty much telling you what we're going to be doing. We're going to be eliminating one of the variables. So let's talk about how we would approach this. So the elimination method says the following. So the elimination method is used by combining equations in order to eliminate a variable. So as mentioned, that's exactly what we're doing. So our goal is to kind of come up with a way where we can combine the equations to get rid of one of the variables. Because if I could get rid of one of the variables, then I'll be able to solve for the remaining variable, and then that would get me the other. Then I would be able to solve for both the x's and the y's, or whatever my two variables are. So here are the steps that we're going to do. The steps we will follow are, so here's what's going to happen. Our first step is multiply, if needed, by the way, so if this is necessary, one or more of the equations by appropriate constants to ensure two of the variables are exact opposites. Okay? And see, if you already start off with a system where two of the variables are already exact opposites, we don't need to do step one. But what is it that we want to do? We want to multiply your equations by two numbers. Now, they don't have to be the same numbers. They could be two different numbers. But we want to make sure that one pair of the variables, or the variables, either the x or the y, they become exact opposites. Now, why do we want them to be exact opposites? Because if they are exact opposites, then what we can do is we can just add them. And when we add them, they will, the opposite variables will cancel out. So we're going to say combine the two equations and solve for the variable. So what's going to happen is when we combine the two equations, it's going to break down to a single variable, and then we could solve for that variable. And then once we do that, then we can go back and find the other variable by substitution. So we would say substitute the value solved in step 2 back into one of the original equations. To complete the solution to the system. So basically what we're saying is once you solve for one of the variables in step 2, then you can go back to any one of the two original equations. It doesn't matter which one. And then you just plug that in, substitute, and then find the other variable, and then that'll complete the solution. Okay, so let's look at our second example where we will use elimination. And in all honesty, it doesn't matter which one of the methods you use, right? You could use elimination or substitution in any one of these problems, and it's not going to make a difference in your solution. So we're going to use elimination here. So we're going to say find all solutions of 5x plus 4y equals to 54, and x minus y equals to negative 18. Okay, so we have options here. See, I could turn either the x's into exact opposites or the y's into exact opposites. So if I want to turn the x's into exact opposites, what would I do? I would multiply everything by negative 5. How come? Because if this is 5x, I want this to be negative 5x. Okay, or what do I notice here? This is 4y and this is negative y. What I could do is I could turn these guys into opposites by multiplying this second row or the second equation by 4, which that's what I'm going to do. So I'm going to take this and multiply this entire row by 4. Okay, now I just happen to choose to turn this into opposites. You could also turn the x's into opposites. It's not going to make a difference as far as our solution goes. So this turns into 5x plus 4y equals to 54, and then this becomes, if I multiply it by 4, I get 4x minus 4y equals, and remember, why could I multiply this whole equation by 4? It is, after all, an equation. So as long as I multiply everything by 4, then that's a valid move. So it's just like a basic algebraic move. So if I multiply this whole row by 4, I get 4x minus 4y, and 18 times 4 is what? Negative 72. Okay, now that I notice that these two y's are exact opposites, then what do I want to do? From step 2, what were we saying? Combine the two equations. So if I add them, what do I get? I get 9x, those cancel out, the y's go away, equals to, and what's 54 minus 72? That's going to be negative 18. Okay, and if it's 9x equals to negative 18, then this, if I divide both sides by 9, which allows me to solve for x, and x is negative 2. And if x is negative 2, now I found the x value of this, so I could come back to the original equation. So let's say I take, what was one of the original equations? X minus y equals to negative 18. I could replace x with negative 2. So we know that then replace x with negative 2 here. We get negative 2 minus y equals to negative 18. And then we solve for y. So if I add 2 to both sides, I get negative y equals to negative 16. And then if I multiply both sides by negative 1, I get y equals to 16. So my solution here is what? Negative 2 comma 16. So once again, we had a single solution. Okay, so we're almost done. I want to do a few more examples, but the last method, which we're not going to do an example of this because this is finding solutions through the graphical method, which simply put, how do we find solutions of a system by graphing through the graphical method? So it's just literally what? That this method is solved by graphing both linear equations and locating the point in which they intersect. Okay, so keep in mind that they may never intersect, and if they don't intersect, then obviously there won't be a solution. They may intersect everywhere, so we might have infinitely many solutions, or if they intersect at one point. So usually we could use a graphing utility to do so, or if it's simple enough lines, we could probably graph it and see exactly where they intersect. Okay, so before we end the notes here, I want to do a couple more examples where we'll see when the case where we have infinitely many solutions and no solutions, and you'll see how the process should not change here. So for example 3, if we have something along the lines of solve the system which is 12x minus 3y equals to 7, and negative 20x plus 5y equals to 4. So what I'm going to do here is I'm going to choose to use the elimination. And I think the easiest way to use elimination is to turn the y's into exact opposites. So right now they have opposing signs, but to make these exact opposites, I would need to multiply this row by 5 and this row by 3. Therefore, this would be a negative 15 and that would be a positive 15. So what I'm going to do is I'm going to say, well, grab the first row and multiply it by 5, and grab the second row and multiply it by 3. And notice how the 5 and the 3, none of them should be negative because these are already opposing in signs. So if this was a positive 3y, then I would have to multiply it by a negative 5, so I would make the signs be opposite. But in this case, we can then say, what does my system change to? If I multiply the first row by 5, I get 60x minus 15y equals to 35. And then the second row turns into what? Negative 60x plus 15y equals to 12. And now I'm actually noticing, and see how this process is, without noticing how many solutions we have, we notice that actually this ends up being what? Both the x's and y's ended up being exact opposites. So when I add them, what do I get? 60x minus 60x, that becomes 0, plus negative 15y plus 15y, that's 0, equals to 35 plus 12, which is 47. So what is it that I get? I get 0 equals to 47. And sure enough, going through this process, I noticed that I got a result here that makes no sense whatsoever, because 0 is clearly not the same thing as 47. So this is suggesting that what? We have something that makes no sense, which means this system has no solution. Or in other words, if I were to graph these, you'd see that these are two different lines that are parallel. They will never intersect. So we would say that this is inconsistent, or you could say it's no solution. Okay, so that's literally, so notice how before I solved this, I didn't know how many solutions I had, if any. But through the process of elimination, I noticed that both variables canceled out, right? So in this case, since I got an equation that makes no sense, it became inconsistent. And then you'll see how for infinitely many solutions, something similar will happen, but then it won't be something where it's like this, where it makes no sense. And so let's actually talk about another example where you'll see the case for the infinitely many cases or infinitely many solutions and we'll go from, and then we'll wrap up the notes here. So if I said solve the system, something along the lines of 2x minus 6y equals to 24, and 3x minus 9y equals to 36, I'm going to go ahead and use elimination again. So I'm going to make the x's opposite. So since they both have the same sign, I just need to make sure one of them is multiplied by a negative number. So if this is 2x, I need to multiply it by a 3, so I'll multiply everything by a negative 3, and this is a 3x, I'll multiply everything by a 2, so I'm literally multiplying these guys to get 6. So if I do that, what do I get here? I get negative 6x plus 18y equals to 24 times 3, that's going to be negative 72. And then what do I get down here? I get 6x minus 18y equals to 72. And notice how these are exact opposites, which now if I add them, so same thing is happening in example 3, except now what's going to happen, I'm going to get something that makes sense. So if I add these, I get 0 plus 0 equals to 0, which then what does this mean? I get 0 equals to 0, which if you compare this to the previous example, I'm getting something that's absolutely true. But notice how when you get a number equals a number, which is, or the same number in this case, what is this saying? This is suggesting that we have what? We have infinitely many solutions, which is dependent. Now, we don't want to say this has infinitely many solutions because we don't want to be misleading. There's a way of showing how these are infinitely many solutions, because when you say infinitely many solutions, then my question is going to be, well, is 0, 0 a solution? And the answer is no. So how we need to do this is we need to free up a variable. So take any one of these equations. So I'll take the first one. So, and it doesn't matter which one of the two you pick. So if I pick the first one, I'm going to say 2x minus 6y equals to 24. And then what I'm going to do is I'm going to free up one of the variables. So I'm going to say, look, for me to get infinitely many solutions, I'm going to pick x, and it doesn't matter, you could pick x or y, but I'm just going to pick x. I'm going to say, let x be any real number. And see, hopefully you'll see why this solution is called dependent. Now, what do I know? Y depends on x. Whatever x is will depend on what y is. So if x is any real number, then we're going to solve for y. Then what does that imply? Negative 6y equals to 24 minus 2x. And if I divide both sides by negative 6, I get y equals to 1/3 x minus 4. Okay, so look at what we're saying. Why do we have infinitely many solutions? Because x can take on any real number. X has infinitely many possible inputs, but y depends on x. So look, when x is 0, y is negative 4. When x is, let's say, I don't know, 3, y is negative 3, and so on. So we could see that earlier how I said, hey, is 0, 0 a solution of this? 0, 0 is absolutely not a solution of this, because when x is 0, y is negative 4. So the correct way of showing that this has infinitely many solutions is we're saying, look, all the points I want are these. It'll be, and maybe I should actually leave some more space. So it'll be x, comma, and that's my x component, and my y component would be what? 1/3 x minus 4. And then if you want, you could also say x is any real number. So what is it that we're noticing here? How many points do I have here? Infinitely many points. And that's how we're saying we have infinitely many solutions, right? Because for each x, I get a specific y. So y depends on x, and that's where it gets the name dependent from. So just keep in mind that if you have infinitely many solutions, I want you to express your solutions in this format. Okay, so that takes care of this section. If there's any questions you have on the notes, don't hesitate to reach out. Let me know if there's anything you need me to clarify. I'll be more than happy to do so. But this takes care of solving a system of linear equations in 2 variables.